In half a second, your nervous system can clamp down a blood vessel. Here's exactly how. It starts at a nerve terminal, sitting right next to the vessel it's about to control. Inside, it's already stocked with tiny packages, ready to fire the moment a signal arrives. But first, that package has to be built. The raw material is a simple amino acid, tyrosine. A chain of enzymes reshapes it, step by step, through two intermediate forms. The final product is norepinephrine, the messenger itself. It gets packed into a vesicle, loaded and waiting. When the impulse hits, calcium rushes into the terminal. That calcium is the trigger. It makes the vesicle fuse with the membrane. Norepinephrine spills out into the gap between the nerve and the vessel. Now, it has to find its target. It locks onto an Alpha-1 receptor on the vessel wall. That flips on a G protein just underneath the membrane, which triggers a burst of second messengers inside the cell. And the vessel wall clamps down, vasoconstriction in real time. But some of that norepinephrine drifts back and binds the nerve terminal itself. It hits an Alpha-2 autoreceptor, a different G protein, a different effect. This one dials things down, telling the terminal to ease off. It's the system's own brake pedal, negative feedback on its own release. The signal has to end somewhere. Most of the norepinephrine gets pulled straight back into the terminal by a reuptake transporter. What's inside gets broken down by MAO. What's left in the gap gets cleared by COMT. Clean shutoff, ready to fire again. Now block that shutoff, and everything changes. Cocaine and tricyclics jam the reuptake transporter. Norepinephrine lingers in the gap, and its effects stretch on. MAO inhibitors jam the breakdown enzyme instead. Norepinephrine builds up inside the terminal. Same messenger, same receptors block the exit, and you get an exaggerated, prolonged sympathetic effect. That's the whole junction start to finish.